So the whole idea behind Taylor series and Maclaurin series is to give a more easy to work with representation of functions like sine x, cosine x, natural log, e to the x. Because with these functions, especially like natural log, we just define them as being the inverse, like natural log is just defined as being the inverse of e to the x. And so to find the value, we have to kind of go around it in like an indirect way. We kind of just want a completely direct way of expressing these expressions. And so how we do that is we use polynomials. So in the case of cosine, we would like to find a polynomial that approximates cosine. And we're going to start off with a quadratic, just ax squared plus bx plus c. And how can we quantify what we mean by approximating? Well, we can look at the graph of cosine. And the graph of our quadratic here is going to be some like U shape. And we want this approximation to kind of hug the cosine graph. Sort of like that. Well, the first thing we're definitely going to want to do is we're going to want the approximation to match cosine at x equals 0, right? At its vertex. And so to do that, we just need to figure out what cosine is at 0, and then just set that equal to our approximation. And so we just set the x in both sides equal to 0. If we do that, we get that cosine of 0 equals 1. And this is going to be exactly equal, not approximately equal, to x being set equal to 0 on this side, which is going to be c. It's exactly equal because that's how we're defining our approximation. And so we found c. How can we find b and a? Well, we can kind of extend this idea, because what we pretty much did is we tried to match our approximation at x equals 0 to be exactly equal to the normal function. And so what we might also want to do is set the derivatives equal to each other. And so we can take the derivative of both sides. On the left side, we get minus sine x, and this is still going to be approximately 2ax plus b. Now, if we set both sides equal to 0, we still cancel out these previous terms, and we're just left with the b coefficient. And so this is a pretty easy way to find b. And so if we set both sides equal to 0, we get minus sine of 0, which is just 0, is exactly equal to b. And so now we found 2 out of the 3 coefficients, and it should be pretty obvious how we're going to find the third. If we take the derivative again, we get minus cosine x equals 2a. And now we just need to set x equal to 0 again. We get minus cosine of 0 equals minus 1, and that's going to be equal exactly to 2a. Or our a coefficient is going to be minus 1 over 2. And so now we're going to combine these two things, and we're going to say that our cosine approximation is going to be 1, which is our c term, minus x squared over 2, because we had no b term, so this middle term cancels out, and the minus 1/2 goes with the a, or the x squared. And so this is going to make a parabola that starts up here and curves down, just like we wanted it to. Now, using a quadratic like this was kind of an arbitrary choice. We could have used any number of terms in our approximation. And so I would want to repeat this process, but with more terms. And so how we're going to write that is we're going to use slightly different notation. We're going to say that cosine x is approximately a null plus a1x plus a2x squared plus a3x cubed, on and on, until we get to some nth term, a to the n, x to the n. And now let's just repeat this process, but let's see how it looks like for an arbitrary amount of terms. If we take the derivative, we get minus sine x is is approximately equal to a1 plus 2a2x plus 3a3 x squared plus dot 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 n a to the n x to the n minus 1. Then let's actually keep track of each of the coefficients. So this first one, if we set x equal to 0 to both sides, we get 0 is equal to, cosine of 0 is equal to 1 is equal to a null. And then for our first derivative, we set sine x to be sine 0 minus sine 0. That's going to be 0, and that's going to give our second coefficient here, a1. So let's repeat this process. We have minus cosine x is approximately 2a2 plus 3 times 2a3x plus on and on until we get to our nth term, which is going to look like this. Okay? So now we can set x equal to 0 to both sides, continuing the pattern like we did before. And all these terms cancel out. This becomes minus 1. So this is minus cosine of 0. And this side becomes 2a2. So it's not just the nth derivative is equal to the nth coefficient. We get this number in front. And we need to figure out what the pattern behind that number is. It's not too hard to see once you do it many more times, a couple more times. If you take the derivative again, you're going to get sine x. It's approximately, well, this term goes out. This becomes 3 times 2, 8, 3, and the x goes out, on and on and on. And actually, I'm going to include the fourth term, which I didn't list before, but it's going to be 4 times 3 times 2, x, a to the 4, a4, x, on and on to our nth term. I've run out of space, but just bear in mind it would be n times n minus 1 times n minus 2, a to the n, n minus 3. And so if we set both sides, or set x equal to 0 for both sides, we get sine of 0 equals 0, and that's equal to 3 times 2, a3. Now, if we do this again, the pattern becomes very clear. We get cosine of x is approximately 4 times 3 times 2, a to the 4, on and on, till we get to n minus 1, and the n minus 2, which we didn't have room for before, and the n minus 3, and then a to the n, x to the n minus 4. And so, for this one we set 0, x to be 0 for both sides, and we get cosine of 0 is equal to 1 is equal to 4 times 3 times 2 times a4. So the pattern, if it's not obvious for you right now, is that we take the factorial of whatever term we're dealing with. So this is going to be the fourth term, so we're going to be 4 factorial. And it's going to be the fourth term in terms of 0 to on. So in reality it's the fifth term, but we numbered it as 4. And so this one's going to be 3 factorial, this one's going to be 2 factorial, this coefficient is going to be 1 or 1 factorial, and this one's actually going to be 0 factorial, which is also 1. And so that pattern is going to continue, and we can see that it continues, because if we took the nth derivative, which we write as cosine x, nth derivative with the parentheses, it's going to be n minus 1, n minus 2, on and on, until we get to 1. And that's just going to be n factorial, a to the n. And once we've done the nth derivative, we just have the coefficient. We don't have the x anymore, as we can see from the pattern before. With the first derivative, the first coefficient ordered, or the coefficient 1, is isolated. With the second derivative, it's coefficient 2 is isolated. With the third, it's coefficient 3. And so for nth derivative, the coefficient n is going to be isolated. And so we could solve for the nth derivative by just dividing over the n factorial. And so we can just, if we continue this pattern, we can write it like cosine x, nth derivative is equal to n factorial. Now, from the way I wrote it, we ended with the nth term, but we could have kept going. And if we kept going, all the terms past this would have contained an x, as we can see from before. There's the isolated term, and then there's the terms with the higher powers, and so they keep their x's. And so if we set x equal to 0, and if we set x equal to 0 on this side, all these will cancel out, and we'll have the isolated term. And so this is actually going to be the nth derivative of cosine at 0. And so you might have noticed a pattern with cosine here. With the derivatives, we get 1, 0, minus 1, 0, 1. And notice that at this point we started back to where we were at the beginning. And so the derivative of this is going to be this again. The second derivative is going to be that again, and on and on and on. And so it's going to cycle between these. And so this is some alternating signs pattern. And so maybe we can actually express the nth derivative of cosine. Now, it gets a little tricky because we have these middle terms that are just 0. The odd terms are going to be 0, so we only have to consider the even terms. And so let's say I've been using n. N is just counting numbers. It goes from 0 to 1, 2, 3, 4, 5, on and on. And we write it as n is going to be element of the natural numbers, which is just 0, 1, 2, 3, 4, on and on and on. And we're only concerned with the even powers, the even coefficients. And the reason why that's important is because the factorial is associated with what term it is. And so it's not enough just to say n factorial, because if we did that, our first term will be good, but for our second term, we'll get 1 factorial when it has to be 2 factorial. So the way we write this is that a to the 2n. 2n is going to be even numbers, right? 0 times 2 is 0, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, on and on, just all the even numbers. It's going to be the nth derivative, which we can see the pattern goes 1, minus 1, 1. And we can write this as minus 1 to the nth power, right? Because we start with 0, that's just 1. First power is minus 1, second power is 1, on and on. It alternates. And if we put just n and nothing special, because we're only considering the even powers. And we're going to put this over 2n factorial, because it's just the even powers that we're considering. And so what we can do is for this we've assumed finite amount of terms, but we can extend this to an infinite amount of terms, because you can see that as we add more terms, our approximation gets closer and closer and closer. And so we say at infinity, the approximation becomes the function. And so we can write this as a sum, an infinite sum, because we just have things being added on, and we have this pattern here. And so we say that cosine x is the infinite sum running from n equals 0 to infinity. This is going to be the coefficients in front of each term. And now each term is going to be the even powers, right? Because we're considering the even coefficients. And you can see that each coefficient name is associated with the power. And so we can write cosine of x as the infinite sum running from n equals 0 of minus 1 to the n over 2n factorial times x to the 2n. Now our choice to use cosine is kind of arbitrary, right? Because the process we did is not special to cosine. We could have done it with any function. And so this idea of applying the derivative repeatedly to get not just an approximation, if you do it infinitely, you get the exact function is called a Taylor series. And so how it's written is we can kind of use this idea, but instead of just being cosine x, it's just any function. To find the coefficients of each term of our infinite series, we take the nth derivative, which we're going to write generally like this, and we're actually going to put it to 0, not just x, and we're going to put it over n factorial, and not just the even ones, because the even ones was just specific to cosine. If you look at the Taylor series for sine, it's actually the opposite. It's only the odd terms that get added. But for general functions, it can be any of the numbers, and that gets multiplied. Each of those terms get multiplied by x to the n, and so that's what's known as a Taylor series. But you might notice that even our choice to use 0 to determine the behavior of the function, to use to center it at 0, is kind of arbitrary. We could have used any other point. Right? Why couldn't we use, let's say, a point C and determined all the derivatives of the cosine at that C and then use that in our approximation? Well, the only problem with that is that if we plugged C back into our function, it would no longer cancel out. What was nice about 0 is that when we plugged in 0 to all of these, it would isolate the term we were looking for. But there's a pretty easy fix, right? So before we had a general case, a to the n, x to the n. And if we plugged in c, it would just be some number. To fix this, we can just change our x term to be x minus c. Now notice that this doesn't really affect the derivative too much, right? Because the inside term, the derivative of the inside term is just 1. So chain rule is not going to change this derivative. And if we plug in c, this becomes 0, and the behavior we had before where it would wipe out the previous terms holds. And so a more general Taylor series is called a Maclaurin series, and it's written like this. It looks very similar, but instead of having the nth derivative of f at 0, we have it at c, and each term is x minus c to the n. And so those are this is the Taylor series, this is the Maclaurin series. I don't think that's how you spell Maclaurin, but whatever. And so they're very useful in maths, obviously for approximating functions. They're quite nice, but just having the ability to express these functions using polynomials makes them a lot easier to work with. And they're even used most famously to prove Euler's identity, e to the pi I equals minus 1. We're not going to do that today. So yeah, those are Taylor and Maclaurin series, or general functions. You also have to prove the convergence of the series before you can really use them. For sine, cosine, and e to the x, their Taylor and Maclaurin series converges for all real numbers. But like for natural log, that one only converges from like either, I think, -1 to 1. And so yeah, you need to be careful about when these converge, because if they don't converge, they don't approximate the function. So yeah.